everyone. Myself, Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So, in today's class, we are going to discuss the concept of self and mutual inductance. So, in the previous class, we have already discussed some basics about the magnetic circuits. Okay, so which means especially we have discussed in the magnetic circuits what is the Faraday's law of electromagnetic induction. So, and in extension of this, here in today's class we are going to discuss about the concept of self and mutual inductance. So we already know about the inductance. Okay, so how we can represent the inductance. Okay, what is inductance, and the inductance will depends on what kind of parameters that we have already discussed. So in just before that, okay, so let me again recall what is meant by these inductance. So here, as you can see, the induction in the magnetic field, which is proportional to the rate of change of the magnetic field. So which means here, the induction which is proportional to the rate of change of the magnetic field. So when there is a rate of change of magnetic field, okay, so then only the current will flowing through that particular conductor, right? So then this the induction, okay, which is also known as the inductance, and which can be represented with a letter, the capital L, and we know the units for these inductance here, it is Henry. Okay, and there are various factors that affect the inductance of the inductor. So here the factors that affect the inductance of the inductor, here it is the number of turns of the wire used for the inductor, because which means the coil is nothing but when a wire, okay, which is turn around a particular conductor, then we can call it as a coil. So which means the amount of inductance is depends on the number of turns of that particular coil or the wire used in that particular inductor, and also the material used for the core. The core is nothing but the conductor, okay, so which is used, and here the inductance value is also depends on the type of the material which is which we are using for the inductor, and also the shape of the core is also affect the value of the inductance, right? So actually, of course, here there is a formula that they have written, that I have written, because already we have discussed about this particular equation in the Faraday's law of electromagnetic induction. So which means here, which is nothing but the electromotive force, which is EMF, or simply we can also call it as a the voltage, which is equal to minus L into di by dt, or delta I by dt. So delta I is nothing but the change in current, and delta T is nothing but the change in time. So here L is the inductance, okay, of that particular coil. Then coming to the concept of self and mutual inductance, right? So here, of course, as you can see, there are two pictures that you can see, the left side and right side. So let me consider, here it is 1 and here it is 2. So here the name itself, as you can see, self-induction, right? So if you want to produce the inductance of a coil, then you must have a coil, right? So the self-induction is nothing but the EMF induced by the coil is linking the coil itself. So that is called as a self-inductance. So for that, here one coil is enough. And when coming to the mutual inductance, here you need two coils. Okay, so which means the EMF induced in the coil, okay, linking with the secondary coil, then which is called as the mutual induction. Or maybe the EMF induced in the secondary coil will link with the primary coil, or the coil A and coil B, which means here this is about the mutual inductance, self-inductance and the mutual inductance. So let us discuss in detail about what is self-inductance and what is mutual inductance, which means what are the properties of the coil in the self-inductance, and what are the properties of the coil in the mutual inductance based on the various parameters. So first, let us go with the self-induction, right? So here The self-induction means the coil induces the EMF themselves. So that is called as a self-induction, right? So the self-induction means the coil induces the EMF themselves. Okay. So then there is a change in the magnetic flux through the coil because of the EMF induced in the coil itself, right? So first of all, the self-inductance is nothing but the what is that the coil induced EMF themselves, okay, or in the coil itself, that is called the self-inductance. And because of the EMF induced in that coil, okay, so there is a change in the magnetic flux through that particular coil, and because of this change in the magnetic flux, the current will be induced in that coil by itself, which means the current will flow through that coil. Okay, so which means once the current get induced, the current will opposes the flux, because we have already learned the Lenz law. Okay, so the Lenz law, according to the Lenz law, okay, so the EMF induced in the coil will oppose the current flowing through that particular coil, right? So how here the current is flowing through the coil? Because of the change in the flux or the change in the field, right? So which means both vice versa. Okay, so which means the current opposes the flux or the flux opposes the current. So both are in opposite direction. Okay, so that's why in the previous case we have seen the equation for the EMF, okay, which is electromotive force, which is equal to minus L into di by dt. Okay, so here the minus sign represents the current flowing through the coil or the current induced in the coil, okay, opposes the flow of flux. That's why there we indicated with the minus sign, right? So, or otherwise, when there is a change in the current or the magnetic flux of the coil, an opposite induced electromotive force is produced, which is called as we usually represented with as a EMF, right? So, this particular phenomena is called as the self-inductance. So here, as you can see, this relation, this phi is directly proportional to the current, which means the flux or the field, okay, is directly proportional to the current induced in the EMF. Because how the current is induced or how the current is flowing through the, or what is the reason the current flowing through the coil, where it is, there is a change in magnetic flux. Okay, so the amount of the current which is flowing through the coil is depends on the strength of the magnetic field or the flux, so which we usually represented as a phi. So that's why here the phi is directly proportional to I. When the phi is increasing, then the current flowing through that particular coil is also getting increased, right? So this is about the phenomena or the concept of the self induction, right? Then when coming to the if you want to derive, okay, so what is the actually the EMF produced by this particular coil, okay, and or the relation between the EMF produced by this coil with respect to the current and as well as with respect to the change in the flux, right? So here, as we know, the EMF induced in the coil, how the EMF is induced in this coil? Because of the rate of change of flux, right? And the EMF induced in the coil is depends on the number of turns also. Okay, so that's why here let us consider this equation. Okay, so the rate, the EMF induced in the coil with respect to the rate of change of flux, which is represented by here minus N into d phi by dt, and the EMF equation that we have already know, which is EMF is equal to minus L into di by dt, because here the EMF induced in the coil because of the current flowing through the coil, or this opposes the EMF induced in that coil. So here it is minus L into di by dt. So both represents the voltage across the coil, or the EMF induced in the coil, or the EMF induced across the coil. So let us consider this is equation number 1 and this is equation number 2. Then equate the equation number 1 and 2, because both are representing the EMF the EMF induced across the coil. So then if you equate here, okay, so if you equate and then simplify this, then minus gets cancelled, then the inductance of the particular coil L is equal to N into phi by I. So here N is the number of turns, okay, the number of turns of that particular coil, and here the phi is the magnetic flux, and I is the current flowing through that particular coil, right? Then here L we can also call it as a not just a simple inductance, okay. So the L is called as a self inductance, okay. So L is the self inductance, because in the next case we will discuss the mutual inductance, okay. So just to differentiate the inductance produced, I mean the inductance of the coil in the single and the mutual, okay. So then L is here, it is called as a self inductance, right? So as I mentioned here, the voltage generated is always opposes the current flowing through the coil, okay. So that's why here because this we have already discussed in the Faraday's law of electromagnetic induction also. So that's why here I have just mentioned according to the Lenz law, here we are getting the minus sign, right? So this is about the concept of the self inductance. Then coming to the concept of mutual induction, okay, self induction and the mutual induction. So here for mutual induction, we should have the two coils, okay. So the two coils may be arranged in various ways, right? Because as you can see in this slide, so this is one way, and this is the second way, and this is the third way that the two coils are arranged, okay. So which means the mutual inductance is the interaction of one coil magnetic field on another coil as it induces a voltage in the adjacent coil, okay. Which means here, suppose if you apply some primary current, or if you apply some voltage, okay, or if you supply the voltage across the primary coil, right, then it produces the magnetic field or the flux, and the field or flux, okay, is interacting with the second coil. So because of the change in flux in the second coil, okay, then an EMF is induced in that coil because of the mutual inductance, right? So the mutual inductance between the two coils is defined as the property of the coil due to which it opposes the change of current in the another coil, right? Because according to this mutual inductance, okay, so the voltage which is produced in or the voltage induced across the secondary coil is due to the current flowing through the primary coil, or the change of or the change of current in the primary coil, and the vice versa. Suppose the same case, okay, so if the voltage produced across the primary coil, okay, so due to the change of current in the secondary coil, right? So that is what the mutual induction principle, right? And as we discussed here, of course here you can see, so this is the first coil, okay, and this is the second coil, or simply we can call it as a primary and the secondary. So here this is the coil 1 and this is the coil 2. So which means in this case the current flowing through the coil, okay, will cause the voltage or the EMF produced across the coil 2. Similarly here also, okay, so the current flowing through the coil or the change of current, okay, in the coil 1 is caused to produce the current in the voltage across the coil 2, or the EMF across the coil 2. The same way here also, okay, so one inside another coil that we have placed. Of course there must be you must maintain some air gap between the primary and the secondary coil, or the coil 1 and coil 2, right? And the amount of this mutual induction, okay, or the linking of the flux produced by the primary coil to the secondary coil, or the amount of the flux, okay, produced by the first coil to the secondary coil is depends on the distance between the two coils. If the distance between the two coils is less, then the flux linkage is more, and if the distance between the two coils is very large, then the linkage of the flux between the two coils is less, okay. So that is also very important in case of the mutual inductance, right? So for that here, Let me take one example here. Okay, so here for the simple understanding, so let me take two coils. Okay, so here let us consider this is the primary coil or the coil 1, and this is the coil 2. Okay, so here if you place one or two lines in between the two coils, which means there is a the connection between the coil 1 and coil 2 or the core. Okay, so here let us consider here the current flowing through the coil 1 is I1, and let us consider here the voltage across this coil 1 is V1, and here the number of turns in the coil is N1 and the number of turns in the secondary coil is N2. So let us consider here it is coil 1 and this is coil 2, right? So here, because of the voltage applied across the coil 1, okay, then an EMF induced in this particular coil 1 or the flux it will produce or the change in flux. Because of the change in flux here, the current flowing through the primary coil, okay, and this flux is linking with the secondary coil. So let us consider here this is the flux which is produced in the primary coil is phi1. Then the same flux is linking with the secondary coil. So let us consider here the flux linkage with the secondary coil due to the flux produced by the primary coil. Let us consider here it is phi12, right? So because of the flux, the change in flux phi12 in the secondary coil, an EMF is induced across the secondary coil, which is let us consider as V2, right? Then if you write the equation for the V2, so here V2 which is equal, okay, already we know in the what is that self-inductance, okay, so the EMF or the voltage V is equal to here minus N into d phi by dt, right? So but here N, okay, so because where, I mean, which voltage we are going to find? The voltage across the secondary coil. Then what are the number of turns of the secondary coil? N2 as usually, so here N2. And what is the flux linkage with the secondary coil? Here it is phi12, because here the same amount of flux may or may not be linked with the secondary coil. Because the primary coil, the flux produced by the primary coil is phi1. Okay, so maybe the flux may not be linked with the primary coil. So that's why let us consider the flux linkage with this secondary coil. Here it is, let us consider as a phi12. So here then d phi12 by dt. So let us consider here it is equation number 1, right? And another case, here we know already this what is that the voltage V2 or V, okay, V is directly proportional to the current, okay, flowing through that particular coil, right? So here, but here V2 is directly proportional to, okay, why the EMF is induced in the V2? Because of the change in current in the coil 1, right? So that's why here V2 is directly proportional to di1 by dt, right? Then we can write this one simply. So V2 which is equal to minus M into di1 by dt. So let us consider this is equation number 2. So here M is the mutual inductance. Before we represented in the self-inductance concept, we represented it as a L, but here in the mutual inductance, we are representing it as a M. So this is the mutual inductance. Here M is called as a mutual inductance. So as you can see here, the equation 1 and 2 both are representing V2. Okay, then you can equate equation number 1 equal to 2. So equation number 1 is minus N2 into d phi1 by dt, which is equal to minus M into di1 by dt. So here minus minus gets cancelled. Then finally, here the mutual inductance M is equal to N2 into phi12 by I1, which is the mutual inductance, right? So in the same way, okay, so if let us consider, okay, the another case. So this is, let us consider here it is case 1. Then coming to the case 2, right? In case 2, in this case, let us consider here we are applying the EMF or the voltage across the secondary coil, and because of the change in current in the secondary coil, so there will be a EMF induced in the primary coil, okay, or the first coil, right? So here let us consider, here it is I2 and here it is V2 that we have already applied. Okay, then here the number of turns as usually N2 and here it is N1, right? So then because of the change in the current flowing through the secondary coil, so there will be a here the flux, here it is phi 2, okay, and this flux will link with the primary coil. So let us consider the flux linking with the coil 1, here it is phi 2 1, okay, instead of phi 1 2, here it is phi 2 1. So then because of this the change in flux flowing through this primary coil, of course there will be a EMF induced across the primary coil. Let us consider, here it is V1, because exactly the opposite way of the case 1. So here it is, let us consider, here it is case 2, right? So in this case also, here if you see, what is that again? First of all, let us find V1, okay. So V1, which is equal to minus N1 into d phi 21 by dt, okay, and similarly V2 we can also write it as a minus m into, or if you don't want to get confused, then you can make it here it as a m12, okay. So this is m12, then here you can make it as a m21, because here it is V1. So here V1 is nothing. How we are getting the V1? Because of the change in current in the coil 2. So that's why here M21, which is equal to because of the current flowing through the secondary coil, so di2 by dt, right? So again, just equate these two, then you will get here M21, which is equal to N1 into phi 21 by I2, right? Of course, in both the cases, the M12 may or may not be equal to M21, right? So this is how we can find the mutual inductance, which is M, right? Then here, yeah, that's what here that they have mentioned, yeah, here, okay. So which is nothing but here, just now we have discussed, okay, which is the EMF is equal to minus M into di by dt, minus M into di by dt. So that's what here they have mentioned, okay. So which means yeah, that's what here we took the two coils and we have placed the two coils close to each other, and the first coil we usually call it as a primary coil or the P coil, and the secondary or the second coil we usually call it as a the secondary coil, okay, or the S coil, okay. So like in our first case, so let us connect a battery, okay, to the primary coil, and let us connect a galvanometer to the secondary coil. So which means we are providing an EMF through the battery or the voltage through the battery to the primary side. So because of that, then the flux will induced in the magnetic flux will induce in the primary coil, so that because of that the current will, or the change in current will flow through the primary coil, and the flux will link with the secondary coil, okay. So because of that, again an EMF, that's because of the change in flux, the voltage will produce across the secondary coil, which is which we can get from the galvanometer, okay. So based on that, here we are getting the mutual inductance M, okay. So M is equal to just now we have derived, one is either it is N2 into phi 12 by I1 or N1 into phi 21 by I2, right? So yeah, that's what this the same concept that we have discussed, okay. So here in this case, the M12, which is equal to M21, we can make it as a M, okay. So if you equate M12 and M21, okay, so if you simplify this, then you can get here, of course, the M can also derived, or we can also represent like this. M is equal to here mu naught mu R into N1 N2 into A by L. So the same like in the self-inductance, okay, because in the self-inductance, the L is depends on the same way, one is the number of turns in the coil, okay, and the second one is the area of cross section of the coil, or the type of the core, okay, and the shape of the core also. So the same way here, the mutual inductance also is depends on not only, because here we are having the two coils, okay, so that's why here the mutual inductance will depends on the number of turns in the first coil and the number of turns in the second coil, okay. And here A is the cross sectional area of the core, the same way like in the self-inductance, and here L is equal to length of the coil, the same way in the self-inductance. Okay, so of course here the mu naught and mu are the mu naught is the here the permeability of the free space. Okay, and here mu r is the relative permeability of the soft iron core, which means whatever the material that we are using. So anyway, here we are using the soft iron core, so that's why here we are representing mu r is the relative permeability of the soft iron core, right? So this is about the concept of the mutual inductance. So as you can see here, the coupling coefficient. Okay, so here the coupling coefficient, which is nothing but, okay, of course in both the ways you can represent the coupling coefficient. So one here it is. So the coupling coefficient sometimes here we have represented as a K. Okay, so here K is equal to, it is the ratio of what is the total flux produced by the, suppose let us consider with respect to the coil 1. So the flux linkage with the coil 1, here it is phi 1. Okay, and the flux linkage with the coil 2, because of the flux produced in the coil 1, let us consider here it is phi 1 2. This is K. And suppose in another case, okay, suppose the flux linkage in the coil 2 is phi 2, and the same amount of the flux if it is linked with the coil 1, then here it is, let us consider phi 2 1, right? So which means if, I mean, the range of this coefficient of coupling, which is here 0 less than or equal to K less than or equal to 1. So I mean 0. Okay, so which means here it is, the K is in between the 0 and 1. So which means whatever the amount of the flux produced by the coil 1 is linking, the same amount of the flux is linking with the coil, what is that, coil 2, then the phi 1 2 will become phi 1, then phi 1 gets cancelled, then K. Okay, so in that case the same amount of the voltage also that you will get, so which means V1 is equal to V2. And in the second case also, okay, so whatever the flux produced whatever the magnetic field produced in the coil 2, okay, the same amount of the field is linking with the coil 1, okay, then this phi 2 1 will become phi 2, then again here you will get 1. Or otherwise, if there is no flux linkage with the, I mean, suppose here the phi 1 is the flux produced in the coil 1, okay, if phi 1 2, okay, or if there is no flux linking with the coil 2, okay, then here phi 1 2 is equal to 0, then which means K is equal to 0, which means if K is equal to 0, then there is no voltage induced in the secondary coil due to the flux produced by the primary coil. The same way in the second case also. So that's why here the coefficient of coupling here K, okay, is in between the 0 and 1. And then of course we can derive this coefficient of coupling. Okay, so how we can derive this coefficient of coupling means here, because because before that we have seen, okay, one is N1 into phi 2 1 by I2, which is equal to, and N2 into phi 1 2 by I2. Okay, so if you simplify this, then you will get here M is equal to K into L1 L2, or here the coefficient of coupling K is equal to the mutual inductance M by L1 and L2. So here L1 is the self-inductance of the coil 1 and L2 is the self-inductance of the coil 2. Because anyway, of course, if it is a single coil, okay, so the flux produced by the coil is linking with itself also first. Okay, then after that, I mean, it will link with the secondary coil also. So that's why here the coefficient of coupling K is equal to M into square root of L1 L2. In other words, I mean, from this also we can derive the mutual inductance. So M is equal to K into square root of L1 and L2. So which means here the mutual inductance is also depends on the K. If K is equal to 1, then you will get the high mutual inductance, and if K is equal to less than 1, then, I mean, if K is decreasing, then the amount of the mutual inductance between the two coils will also decrease, right? So this is about the concept of the mutual inductance. So let us discuss one problem on this coefficient of coupling, right? So here let me read first the problem. So consider a solenoid with 500 turns which were wound on an iron core whose relative permeability is 800 a 40 centimeter is the length of the solenoid, and while 3 centimeters is the radius, the change in the current is from 0 to 3 amperes, which means the delta I is 3 amperes, and calculate the average EMF induced for this change in the current for a time of 0.4 seconds. So actually what they have asked, calculate the average EMF induced in the coil. Okay, so first let us write what they are asking us to find. So the EMF induced in that coil. Okay, so here as we know, the EMF let us represent with this. Okay, so which is equal to L into di by dt, right? So here we know the value of di, which is 3 amperes, and we know the value of dt also, which is 0.4 seconds, but we don't know the value of L, right? So we know the equation for L, which is equal to mu into n square into a into I, a into L, or in another words directly we can write here, because here we are having, okay, so the L or M, whatever it may be, okay, because here it is a one coil, so that's why we are making it as a L. If it is a two coil, then we are making it as a M, the mutual inductance. Okay, so which means here mu naught into mu R into because here only one, so that's why instead of N1 and N2, here we are making it as a N square, because N1 equal to N2, N square into pi R square by L. Right. So first let me write the given data. So here the consider a solenoid with 500 turns, so which means N is equal to 500, which are wound an iron core whose relative permeability. So relative permeability is nothing but here it is mu R, which is equal to 800, because anyway mu naught is constant, which is irrespective of the material that we are using. So mu R is equal to 800, and the length of the solenoid is 40 centimeters. So L is equal to 40 centimeters. So which is nothing but 0.4 meters. Then while 3 centimeters is the radius, so R is equal to 3 centimeters, so which is nothing but 0.03 meters. And the change in the current, so which means here a di, or sometimes we can write it as a delta I, which is equal to 3 amperes. And then the current and time, yeah, so the change in time, so sometimes we make it as a dt or delta t, which is equal to 0.4 seconds, right? So then substitute all these values here, then we will get the L value. So L is equal to here mu naught that already we know, so 4 into because here already we have given, so 4 pi into 10 to the power of minus 7, so 4 pi into 10 to the power of minus 7 into mu R, here it is 800, and n square, n is 500, so 500 whole square, into again pi into R, here it is 0.03 square. Okay, so by L, here it is 0.4. So if you simplify this, then you will get the value of the L, here it is 1.77 henries. Then substitute this L value here, then here the EMF, okay, induced in that particular coil, the average EMF induced in that particular coil is equal to here 1.77 into, so again here di is 3 and dt is 0.4 seconds. Then you will get here it is 13.275 volts. So which is the average EMF induced in that particular coil. Okay, so this is how we can find the average EMF induced in that particular coil. Right. So this is all about the concept of the self-inductance and the mutual inductance. Okay, so in the next class, we will discuss about the dot conversion, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.